Hello everyone. In our last video, we talked about how to determine the cost of an algorithm so that we can make an apples to apples comparison between any given algorithm or any two given algorithms. In this video, we're going to take that one step further and we're going to finally get to BigO notation. So if you'll remember, our algorithm from our first video was right here, and we went through and we counted the lines, and we noted that this first line is only read once, and then you can kind of see here that our size of our array is 4. And we go through this for loop, you can see 4 times, and then one extra time just to check at the end, and then exit the loop. So what BigO notation is, what we've kind of chosen as convention is, it's like an upper bound. That's what we're trying to figure out. What's the worst case scenario for how long this algorithm is going to take to run? And let's say we had a really large data set, and this is really common. I mean, you're never going to deal with a data set that's only 4 items long in real life. But Google and some of those companies deal with millions, billions, trillions, really large data sets. And so what we want to look at is how our algorithm function is in, as this is variable, and as n gets really large. And so to do that, we still basically do the same thing. So we're just going to move through. We're going to come up with a formula for this. So we notice the first line is always going to be read once, no matter what. So for a mathematical function, we're just going to put a 1 in. And then we noted that no matter what, it's also always going to check at the end one more time than the size. So we'll go ahead and put in another 1 there. And let's just make it simple. We'll call that 2. All right. And then it's going to read through this data n times. And so our formula for this particular function is just 2 plus n. Now this isn't quite BigO notation, because what we want is like a simplified version so that we can easily understand and compare two things, and we don't want some long mathematical function. So what we do is similar to what you might do if you've taken a calculus class like dominance of power, is that we only look at what happens as n gets really large, as it becomes millions and billions. Adding 2 to it, really, it's pretty small. It's hardly noticeable. And so we actually drop all the constants to determine our BigO notation. So if we wanted to come up with just the runtime for this function, so the run, capital U, so the runtime for this function is n. So this function runs in time n. So we can say that this scales linearly with the input we give this function. Now let's look at a function that we talked about last week, which was bubble sort. And don't worry about the actual function here. The only thing I want you to note is that we have some line. This is read once, so we've got our constant there. So if we were originally making our formula, we'd say 1 plus, we know we're not done yet. And then we see a for loop here. Don't look at all this. Let's say it runs n times. And then we've got a nested for loop, and we'll say that this runs n times as well. And so for each time that this for loop runs, this one's going to run n times. So we end up with n squared right there. And then don't worry again about this if statement. I don't want to make this too complex, but we could say then that bubble sort, using our same technique, we'll drop the constant, runs in n squared time. Now let's say this wasn't bubble sort. Let's say it was, though, 2 nested for loops, fairly simply, and let's say it had a third for loop, but it was not nested. So we'd end up with something like this. And in this situation, we would do basically the same thing. So we'll start over here. We notice we've got a constant, so we've got 1 plus our nested for loops, so we'll call that n squared. And then we've got another for loop, so we're going to say, well, we've got another 1 here, so maybe we change this to 2, and then another for loop. I'm sorry, another for loop here. This is outside the function. This can actually go away. So then we've got n times, because we just determined that the runtime for this function was n. We just copied and pasted it over, so it must be the same. Now, using the same kind of concept, if we think of n getting really large, this n squared is going to get larger so much faster than this n. And I'll explain that. I'll show that graphically in a second. But for BigO notation, what we do is we drop the lowest power, and the only thing we keep is this n squared. Now, if we had n squared plus n squared, then we could combine this and we could say, okay, well, this runs in 2n squared. But usually we just say the coefficient on this even in this situation, we drop it and we just say it's 1. So this runs in n squared, okay? Because again, it's just a property of powers. This is going to grow so much faster than, it doesn't matter what we have out here. If this is 1,000 n squared, as n gets really large, multiplying it by 10,000 is not really going to change the number as a percentage of the total that much. So I hope that makes sense. To help us understand how different functions scale, you'll note later on in the course when you deal with binary search trees and stuff like that, they often try and get like logarithmic time is really good, and is something that we often aim for. So I just want to show you what different functions would look like as a function of time. So in this graph here, our x is the number of inputs that we put in, and our y is the time that takes. So I've got a couple of functions defined here. So this is the case of 2x squared. The situation where you would find a function like this, as you add the number of items that you add to this function, the time it's going to take goes up at a crazy rate. And this would be if you're iterating through each element of some kind of binary data and determining like how many different combinations there were. That would be an example here. So not something practically you're going to use. But if we look at what we had with our bubble sort, when we have n squared, or in this case x, we see that, it's better, but honestly not that much better. And in our third thing here, I just made a note. This function is the same. This is just n log n, or x log x. And in computer science, log base 2 is what's usually used, and it's used so much that usually you'll just see that. Okay, I just had to write this out in a different way because this program didn't like my input. So if we look at that, we see, okay, this is n log n time, and that's what that scales as. And now let's look at n time. So now we see a linear scaling. As our inputs become large, it scales linearly with our input, our time it takes. And then the last thing we're going to look at here is this is our logarithmic time, so log base 2. And you can see as you increase the number of items you're giving a particular function, or rather an algorithm, the time doesn't, look how different these are. If this is hundreds, if not thousands of times different when you're talking about sizes of 250. And when you talk about sizes of millions, you can really see it's kind of crazy. It's hard to wrap your mind around. So I encourage you to make your own chart, and you'll kind of see how valuable it is to have something that scales in logarithmic time as opposed to exponential, and why whenever you're coding, a lot of times, don't do nested for loops if you can help it, because of how much longer it's going to take whenever you're dealing with any normal size of data that you'll deal with in the real world. So I hope this video helps.